Welcome to topic 3 of the gas laws on Charles's law. In Charles's law, the volume of a fixed mass of gas at constant pressure varies directly with the Kelvin temperature. Here's the Charles's law equation. V1 over T1 equals V2 over T2. The V1 and T1 represent the initial conditions of the gas. The V2 and T2 represent the volume and temperature as the final conditions. You must use Kelvin temperature with Charles's law. Here's a little video showing you Charles's law as the temperature of a gas is cooled using liquid nitrogen. Here's another example of Charles's law, a hot air balloon demo. I'm going to forward to the section on Charles's law.
In 1780, Jacques Charles noticed a different relationship between gases and their temperature. If you've ever seen a hot air balloon, you've seen this law in action. When the balloons are laid out, they're totally flat. Instead of blowing the balloon up like a party balloon, they use a giant flame to heat the air inside that envelope. As the air is heated up, the balloon begins to inflate as the gas volume increases. The hotter the gas becomes, the larger the volume, and that's Charles' law. Notice, this law is different from Boyle's. Charles' law is a direct relationship. As the temperature increases, the volume increases as well.
So the liquid nitrogen video and the hot air balloon example are great examples of the direct relationship between temperature and volume. In a hot air balloon, as the temperature increases, the volume of the balloon expands. And as you might remember from earlier in the year, as the volume expands, the density of the balloon would decrease. Once that density is less than that of the surrounding air, the balloon will have lift and take off. To come back down, the pilot simply has to let the temperature of the air cool. And as that volume then will start to decrease, the density would increase and the balloon comes back to the ground. Here's an example problem for Charles' law. A large helium balloon has a volume of 2.5 liters at room temperature, 72 degrees Fahrenheit. What is the volume of the balloon when it is placed on liquid nitrogen, negative 321 degrees Fahrenheit? The pressure is held constant. As we know from Charles's law, if the temperature decreases, in this case significantly, we should see a decrease in the volume of the balloon. Let's try it out. We'll use the equation for Charles' law, V1 over T1 equals V2 over T2. Your algebra teacher might ask you to isolate the unknown variable, in this case the final volume. You can do that using algebra to get the expression V2 equals the final temperature, T2, times the initial volume, V1, over the final temperature, T1. You could then substitute in the values given in the problem and solve for V2. Another method, which I prefer, is to just go ahead and substitute the variables right into the Charles law equation, and then do the algebra to solve. The initial volume was given as 2.5 liters, so I plug that in or substitute for V1. For T1, I'm going to use the Kelvin temperature, 295 Kelvin. V2 is what we're asked to solve for, the final volume of the balloon. And the temperature of liquid nitrogen in Kelvin is 77 Kelvin. I'm going to cross multiply to get rid of the fraction in this example. So I'll have 295 Kelvin times the final volume equals 2.5 liters times 77 Kelvin. Using algebra, I'll isolate V2 by dividing by 295 Kelvin on both sides of the equation. You will need to apply sig fig rules. In this example, the measurement with the fewest sig figs was 2, the 2.5 liters. So we'll need to keep 2 sig figs in our answer. Using your calculator and rounding, you'll get 0.65 liters. Again, because the temperature dropped, we should see a drop in volume. This does agree with Charles' law. Here's a second example problem. We have an expandable container, original volume 3.5 liters, increased from standard temperature, 273 Kelvin, up to 70 degrees Celsius. The question is, what is the new volume? Again, pressure is held constant. This is Charles' law. So we use the Charles' law equation, V1 over T1 equals V2 over T2. We're going to substitute in our known variables. V1, the original volume, is given as 3.5 liters. The original temperature was standard temperature, 273 Kelvin. The final volume is what we're asked to solve for. That's going to be V2. That's our unknown. And the final temperature is given as 70 degrees Celsius. Make sure you do not plug that into this problem. As you know, you must use Kelvin temperature for these problems. So we're going to convert to Kelvin by adding 273, and we get 343 Kelvin. That is the number that must be placed into the problem. You then cross multiply to get rid of the fraction, and we'll be able to use algebra to solve for V2, the final volume. 273 Kelvin times V2 will equal 3.5 liters times 343 Kelvin. We divide both sides by 273 Kelvin. Again, you'll use sig fig rules in your calculator. The least amount of sig figs in the measurements was 2. 3.5 liters has 2 sig figs. So we will round our final answer off to 2 significant figures, 4.4 liters. The answer check would be to apply Charles' law. The temperature increased from 273 to 343. So we should see the volume increase. It did, from 3.5 to 4.4. So that follows Charles' law.